Our universe is vast. It is filled with wonders beyond our wildest dreams. We see galaxies spinning in the dark, each one a collection of billions of stars. We see nebulae, great colorful clouds of gas and dust where new stars are born. We look out into the cosmos, and we see a story unfolding over billions of years. But every story has a beginning. And the beginning of our universe is the greatest mystery of them all. We call this moment the Big Bang. It's a name that suggests a colossal explosion, a single violent event that created everything from nothing. But the reality is far more complex and far more fascinating than that. This is the question that drives cosmologists, the scientists who study the origin and evolution of the universe. They are like detectives, searching for clues left behind from an event that happened nearly 14 billion years ago. The evidence is faint, encoded in the oldest light in the universe and the distribution of galaxies across the sky. When we look at the universe on the largest scales, we find some deeply puzzling features. One of the biggest puzzles is known as the horizon problem. It's like finding that two people on opposite sides of a vast, empty desert have somehow managed to coordinate their outfits perfectly without ever having met or communicated. In the late 1970s and early 1980s, a young physicist named Alan Guth was working on a completely different problem related to particle physics. While exploring these ideas, he stumbled upon something extraordinary. He realized that the physics he was studying could create a state known as a false vacuum, a peculiar high-energy state of empty space. The theory of inflation proposes the existence of a new type of energy field that filled all of space in the first moments of the universe's existence. This hypothetical field is called the inflaton field. You can think of it like a hill. In the very beginning, the universe was perched at the top of this hill. In a state of high energy, the rapid stretching would have smoothed out any initial wrinkles, explaining the uniformity we see. It would also have stretched space-time so much that it became incredibly flat, just like the surface of a balloon appears flat when you inflate it to a gigantic size. It suggests that the seeds of the largest structures in our cosmos were once quantum fluctuations, tiny ripples in the fabric of space-time stretched to cosmic proportions by this period of rapid growth. But in science, a leading theory is never the only theory. Science thrives on debate, on challenge, and on the exploration of alternative ideas. Some physicists are uncomfortable with certain aspects of inflation. This has motivated a search for alternative models that can solve the cosmic puzzles without some of inflation's more speculative baggage. What if the Big Bang was not a beginning, but a bounce? This is the central idea behind a fascinating class of alternative models known as the cyclic universe. In this picture, our universe is a three-dimensional brane, short for membrane, floating in a higher dimensional space. Another brane exists parallel to ours, separated by a tiny gap. Another fascinating alternative to inflation emerges from the esoteric world of string theory. This is the idea of string gas cosmology. String theory is a candidate for a theory of everything, which posits that the fundamental constituents of reality are not point-like particles, but tiny, vibrating, one-dimensional strings. When we place the leading theories side by side, we see two profoundly different stories about our cosmic origins. Inflation theory proposes a singular, explosive start. In stark contrast, the cyclic universe model offers a story not of a beginning, but of an endless cycle of renewal. One of the most profound puzzles of our cosmos is its geometry. Observations tell us with incredible precision that space is flat. Inflation's solution to the flatness problem is one of its most celebrated features. It works through brute force. By taking a tiny patch of space-time and expanding it by an enormous factor, it effectively stretches away any pre-existing curvature. Every galaxy, every star, every planet owes its existence to tiny imperfections in the otherwise smooth early universe. These primordial density fluctuations are the seeds of all cosmic structure. Inflation theory provides a beautifully simple and compelling source, quantum mechanics. It posits that during the phase of hyperexpansion, the inflaton field itself was subject to tiny, unavoidable quantum jitters. The most powerful piece of evidence we have about the early universe is a faint glow of light that fills the entire sky. It's called the cosmic microwave background, or CMB. Our telescopes, like the COBE, WMAP, and Planck satellites, have mapped this radiation with incredible precision. They have confirmed the first key piece of evidence. The CMB is astonishingly uniform in temperature. While the temperature map of the CMB provides strong support for inflation, there is another, even more definitive signal that cosmologists are hunting for, a specific type of polarization in the CMB light known as B modes. The hunt has been filled with drama and difficulty. In 2014, the BICEP2 team announced a potential detection of this very signal, a discovery that made headlines around the world. However, further analysis revealed that the signal was not from the early universe after all. Instead, it was caused by interstellar dust within our own Milky Way galaxy. Despite this setback, the search continues with renewed vigor and more powerful instruments. The future Lightbird satellite, a joint mission between Japan, Europe, and the US, is designed specifically for this purpose. So after examining the evidence, where do we find ourselves in this grand cosmic debate? The current situation can be summarized simply: inflation has the lead, but the race is not yet over. The theory of cosmic inflation sits in a position of remarkable strength. It not only solves the horizon and flatness problems elegantly, but its core predictions have been confirmed with breathtaking precision. We stand at a remarkable moment in the human quest for understanding. For millennia, the origin of our universe was a question for myth, philosophy, and religion. Today, it is a vibrant field of scientific inquiry. The next generation of surveys and detectors will sharpen our view of the infant universe. They may finally uncover the primordial gravitational waves, sealing the deal for inflation. This cosmic detective story is about more than just finding the right equations or the correct model. It is a reflection of our innate human curiosity, the relentless drive to ask why. The mysteries of the Big Bang are not just abstract puzzles for physicists. They are part of a shared human heritage, a story that belongs to all of us. The endless fascination lies not just in finding the answers, but in the journey of the search itself.